The Internet. The Internet is a vast and intricate network that interconnects millions of computers globally, enabling the exchange of data, ideas, and communication across vast distances. Originating from research projects in the mid-20th century, the Internet has evolved into a critical infrastructure that supports almost every aspect of modern life. It facilitates information access, social interactions, business transactions, entertainment, and more. With the advent of technologies like broadband, Wi-Fi, and mobile data, the Internet has become increasingly accessible, impacting societies and economies worldwide. From search engines and social media platforms to online shopping and cloud computing, the Internet's influence is profound and continually expanding, making it an indispensable part of the contemporary world. The Internet has evolved significantly since its inception, transforming from a military communication tool to a global network that connects billions of people. Let's take a look at a timeline of its development. 1960s. 1965, MIT, Massachusetts Institute of Technology, develops packet switching technology, allowing data to be sent in small blocks called packets. MIT is a prestigious private research university located in Cambridge, Massachusetts, known for its cutting-edge research and education in science, engineering, and technology. Packet switching technology is a method of data transmission where messages are divided into smaller packets. Each packet is sent independently over the network and reassembled at the destination. This approach optimizes network resource usage and allows for efficient and reliable data transfer. It contrasts with circuit switching, where a dedicated communication path is established for the entire duration of the transmission. 1969, ARPANET, Advanced Research Projects Agency Network, the precursor to the Internet, is created by the U.S. Department of Defense. The first message is sent between computers at UCLA, University of California, Los Angeles, and Stanford. ARPANET was the first operational packet switching network and is considered the precursor to the modern Internet. Developed by the U.S. Department of Defense's ARPA, and now DARPA, in the late 1960s, ARPANET aimed to enable secure and reliable communication between research institutions. It laid the foundation for the development of Internet protocols and networking technologies. UCLA is a renowned public research university in Los Angeles, California, which played a significant role in the early development of the Internet. 1970s. 1971, Ray Tomlinson develops email and introduces the @ symbol to separate usernames from computer names. Email is a method of exchanging digital messages over the Internet, allowing users to send and receive text, documents, images, and other files. 1972, the first international connections to ARPANET are established, linking computers in the UK and Norway. 1973. The term Internet is coined to describe a network of interconnected networks. 1974, the first Internet Service Provider, ISP, is launched, offering commercial access to ARPANET. An ISP is a company or organization that provides individuals and businesses access to the Internet. 1980s. 1983, the Domain Name System, DNS, is introduced, allowing users to access websites using easy-to-remember domain names instead of numerical IP addresses. DNS is a hierarchical system that translates human-readable domain names into numerical IP addresses used for locating and identifying devices on networks. 1989, Tim Berners-Lee invents the World Wide Web, revolutionizing how information is shared and accessed. The World Wide Web, WWW, is a system of interlinked hypertext documents accessed via the Internet, using web browsers to display content such as text, images, and videos. 1990s. 1991, the first web browser, called World Wide Web, later renamed Nexus, is released. 1993, the Mosaic web browser is launched, making the Internet more accessible to the general public. 1995, the commercialization of the Internet begins, with the launch of major online services like Amazon and eBay. 2000s. 2004, social media platforms like Facebook and YouTube are launched, changing how people communicate and share content. 2007, the iPhone is released, popularizing mobile Internet access and leading to the rise of mobile apps. 2010s. 2010, the first 4G networks are deployed, significantly increasing mobile internet speeds. 4G, fourth-generation, networks provide higher data transfer speeds and improved reliability compared to 3G. 2016, the Internet of Things, IoT, becomes more prominent, connecting everyday devices to the Internet. IoT refers to the network of interconnected devices that communicate and share data with each other over the Internet. 2020s. 2020, the rollout of 5G technology begins, offering even faster internet speeds and lower latency. 5G, fifth generation, networks offer faster speeds, lower latency, and greater connectivity, supporting a larger number of devices and enabling advancements in technologies like IoT and autonomous vehicles. 2023, nearly two-thirds of the world's population uses the Internet, highlighting its global impact. The Internet's journey from a research project to a global phenomenon showcases the rapid pace of technological innovation and its profound impact on society. As we delve into the rich history and milestones of the Internet, it's essential to understand how this global network actually operates on a technical level. How the Internet works. The Internet is a complex system composed of interconnected networks that communicate using standardized protocols. Here's a detailed explanation of its core components and functions. 1. Internet Protocol, IP. The backbone of Internet communication, IP assigns unique addresses to each device, ensuring that data packets are correctly routed from source to destination across diverse networks. 2. Domain Name System, DNS. DNS translates user-friendly domain names into IP addresses, making it easier for users to access websites. It functions like a directory service, ensuring that the human-readable addresses are converted to machine-readable formats required for routing data. 3. Routing and routers. Routers use IP addresses to determine the best path for data packets to travel. They are crucial for directing packets between networks, ensuring that data reaches its intended destination efficiently. Routing protocols like BGP help routers manage paths and make optimal routing decisions. 4. Transmission Control Protocol, TCP. TCP ensures the reliable transmission of data over the Internet. It handles packet sequencing, error detection, and retransmission, ensuring that data is accurately received and reassembled at its destination, providing a stable communication channel. 5. Hypertext Transfer Protocol, HTTP or HTTPS. HTTP/HTTPS protocols facilitate the transfer of web pages and online content between servers and browsers. HTTPS, with its encryption, ensures secure communication, protecting data from interception and tampering. 6. Internet Service Providers, ISPs. ISPs connect users to the Internet, providing the necessary infrastructure for data transmission. They manage the physical and virtual connections between end users and the global network, enabling access to online services and content. 7. Satellite networks. Role and function. Satellite networks play a crucial role in providing Internet connectivity, especially in remote and rural areas where traditional infrastructure may be lacking. Satellites in geostationary, medium, and low Earth orbits, GEO, MEO, LEO, beam Internet signals to ground stations and directly to users. Implementation. Companies like SpaceX, Starlink, OneWeb, and others deploy constellations of satellites to offer high-speed Internet access globally. These networks use advanced technologies to ensure low latency and high throughput. Benefits. Global coverage. Satellite networks can reach areas that are difficult to serve with traditional fiber or cable networks. Emergency connectivity. They provide reliable Internet access during natural disasters or in areas with damaged infrastructure. 8. Modems and network interfaces. Modems and network interfaces enable devices to connect to the Internet. Modems translate digital data into signals suitable for transmission over various media, e.g., phone lines, cables, while network interfaces, NICs, manage the connection between devices and the network. 9. Web browsers and servers. Web browsers serve as the interface for users to interact with the Internet, sending HTTP/HTTPS requests to servers, which host and deliver web content. Servers respond to these requests, allowing users to view and navigate websites. 10. Data centers and cloud services. Data centers house the servers and infrastructure that host online services, applications, and data. Cloud services leverage these data centers to provide scalable and flexible access to resources and storage, enabling efficient data management and accessibility. 11. Content delivery networks, CDNs. CDNs distribute content across multiple servers globally, reducing the distance data must travel to reach users. This improves load times and reliability, ensuring a smoother and faster user experience. In essence, each of these components plays a vital role in the overall functionality of the Internet. The IP ensures correct addressing, DNS simplifies navigation, Reuters direct traffic, TCP guarantees reliability, and HTTPS facilitates content transfer. ISPs, modems, and network interfaces connect users to this complex system, while browsers and servers handle the user-facing aspects. Data centers and CDNs ensure efficient and scalable data management and delivery, creating a harmonious and effective global network. It's the seamless integration and interaction of these components that make the Internet such a powerful and ubiquitous tool in our daily lives. As we've explored the intricate workings of the Internet and its foundational technologies, let's now turn our attention to 5G technology, the next leap in wireless communication that promises to revolutionize connectivity with unprecedented speed, reduced latency, and enhanced capacity, shaping the future of how we interact with the digital world. What makes 5G so special? 1. Enhanced speed. One of the most striking features of 5G is its tremendous increase in data transmission speeds. 5G networks can achieve speeds up to 100 times faster than 4G, with theoretical peak speeds reaching up to 20 gigabits per second. This means downloading a high-definition movie can take just a few seconds, dramatically reducing wait times and enhancing user experience. 2. Low latency. Latency refers to the time it takes for data to travel from its source to its destination. 5G technology significantly reduces latency to as low as 1 millisecond, making real-time applications like online gaming, autonomous vehicles, and remote surgery more feasible and reliable. 3. Higher capacity. 5G can support a vastly higher number of connected devices compared to its predecessors. This is particularly important for the Internet of Things, IoT, where billions of devices, from smart home gadgets to industrial sensors, can operate simultaneously without network congestion. For improved efficiency, 5G networks are designed to be more energy efficient, providing longer battery life for devices and reducing overall power consumption. This efficiency is critical for maintaining the sustainability and performance of large-scale IoT deployments. 5. Network slicing. 5G introduces the concept of network slicing, which allows operators to create multiple virtual networks within a single physical 5G network. Each slice can be tailored to meet the specific requirements of different applications or services, such as high-speed gaming, ultra-reliable communication, or massive IoT connectivity. 6. Enhanced reliability. 5G networks are built to be more resilient, providing consistent and reliable connectivity even in challenging environments, such as densely populated urban areas or remote rural locations. 7. Massive MIMO. Multiple input, multiple output. 5G uses massive MIMO technology, which employs multiple antennas to transmit and receive more data simultaneously. This increases network capacity and improves performance, especially in high-demand areas. 8. Beamforming. This advanced signal processing technique directs signals to specific users, reducing interference and improving signal quality and speed. Beamforming enhances the overall efficiency and effectiveness of 5G networks. These features collectively make 5G a revolutionary advancement in wireless communication, offering unparalleled speed, reliability, and capacity. As we further explore 5G technology, we'll delve into its core principles and understand how these innovative features are implemented to transform connectivity. Core principles of 5G technology. 1. Enhanced mobile broadband, eMBB. Implementation. eMBB focuses on providing significantly faster data rates and higher capacity compared to previous generations. This is achieved through the use of higher frequency bands, known as millimeter waves, which offer greater bandwidth. Impact: this enables applications like high-definition video streaming, virtual reality, VR, and augmented reality, AR, to be accessed seamlessly on mobile devices. 2. Ultra-reliable low-latency communications, URLLC. Implementation: URLLC aims to reduce latency to as low as 1 millisecond, ensuring real-time communication. This is achieved by optimizing network architecture, such as edge computing, where data processing occurs closer to the user. Impact: critical applications such as autonomous vehicles, remote surgery, and industrial automation benefit from near-instantaneous data transmission, enhancing safety and reliability. 3. Massive Machine-Type Communications, MMTC. Implementation: MMTC focuses on connecting a vast number of IoT devices efficiently. This is made possible through technologies like Narrowband IoT, NB-IoT, and Cat-M1, which allow for low-power, wide-area network connectivity. Impact: this supports the deployment of smart cities, smart agriculture, and industrial IoT applications, where thousands of sensors and devices need to communicate simultaneously. 4. Massive MIMO, multiple input, multiple output. Implementation: massive MIMO involves using a large number of antennas at base stations to transmit and receive more data simultaneously. This improves spectral efficiency and increases network capacity. Impact: it enhances the performance and reliability of 5G networks, particularly in densely populated areas, by managing and distributing the traffic load more effectively. 5. Beamforming. Implementation: beamforming directs wireless signals towards specific devices rather than broadcasting them in all directions. This is achieved through advanced antenna technology and signal processing algorithms. Impact: it improves signal strength, reduces interference, and enhances data transfer speeds, ensuring a better user experience even in crowded environments. 6. Network slicing. Implementation: network slicing allows the creation of multiple virtual networks on a single physical 5G infrastructure. Each slice can be customized to meet the specific needs of different applications or services. Impact: this enables operators to provide tailored services, optimizing resources for various use cases like high-speed mobile broadband, low-latency critical communications, and massive IoT connectivity. 7. Edge computing. Implementation: edge computing brings data processing closer to the user by utilizing local servers or devices, reducing the distance data must travel. This is integrated into the 5G network architecture. Impact: it reduces latency and improves the performance of applications that require real-time processing, such as autonomous driving, gaming, and AR/VR. By leveraging these core principles, 5G technology offers a robust and versatile network capable of supporting a wide range of applications and services. Its implementation drives innovation and transforms the way we interact with technology, making it an integral part of the future digital landscape. Having highlighted the unique features that make 5G stand out, it's crucial to understand how spectrum utilization plays a pivotal role in achieving these advancements. Spectrum utilization in 5G. Spectrum utilization refers to the management and allocation of frequency bands used for transmitting data over wireless networks. In 5G technology, spectrum utilization is critical to delivering its promise of enhanced speed, capacity, and efficiency. Here's a detailed look at how it works. 1. Millimeter waves. Millimeter wave. Frequency bands. 5G utilizes higher frequency bands, specifically in the millimeter wave range, 30 GHz to 300 GHz. These bands provide significantly more bandwidth compared to the lower frequency bands used in previous generations. Benefits: millimeter waves can carry more data at faster speeds, enabling high-definition streaming, augmented reality, AR, and virtual reality, VR, applications. Challenges: the higher frequency waves have shorter ranges and are more susceptible to obstacles like buildings and trees. To overcome this, 5G networks rely on a dense deployment of small cells and advanced beamforming techniques. 2. Sub-6 GHz bands. Frequency bands. These bands operate below 6 GHz, including frequencies used in previous generations, such as 2.5 GHz, 3.5 GHz, and 4.9 GHz. Benefits: sub-6 GHz bands provide better coverage and penetration through buildings, ensuring reliable connectivity in both urban and rural areas. They are essential for maintaining a robust and consistent network. Usage: these frequencies are crucial for wide area coverage and are often used in combination with millimeter waves to balance capacity and coverage. 3. Spectrum sharing. Dynamic spectrum sharing (DSS) allows 5G to share the same frequency bands with existing 4G networks. This enables a smooth transition to 5G without the need for new spectrum allocations, maximizing the use of available resources. Benefits: it ensures backward compatibility and efficient utilization of the spectrum, allowing for gradual deployment of 5G services alongside 4G. 4. Carrier aggregation. Concept: carrier aggregation combines multiple frequency bands to create a larger bandwidth, enhancing data speeds and network performance. Benefits: it improves the overall capacity and efficiency of the network, allowing for faster and more reliable connections, especially in high-demand areas. 5. Licensed versus unlicensed spectrum. Licensed spectrum: these are frequency bands allocated exclusively to mobile operators through government auctions or regulatory bodies. Licensed spectrum ensures less interference and better quality of service. Unlicensed spectrum: these bands are open for use by any device without a specific license, such as Wi-Fi frequencies. 5G can utilize unlicensed spectrum to offload traffic from the licensed bands, improving overall network efficiency. 6. Spectrum efficiency. Techniques: advanced techniques like MIMO, multiple input multiple output, and beamforming are employed to enhance spectrum efficiency. These technologies allow the network to transmit more data over the same frequency bands, improving capacity and reducing latency. Impact: spectrum efficiency ensures that the available spectrum is used optimally, supporting a higher number of simultaneous connections and providing better service quality. By effectively utilizing different spectrum bands and employing advanced technologies, 5G achieves its remarkable capabilities, setting the stage for a new era of connectivity. This sophisticated spectrum management ensures that 5G networks can deliver ultra-fast speeds, low latency, and high capacity, transforming how we connect and interact with the digital world. Understanding the role of spectrum utilization sets the stage for exploring another critical aspect of 5G technology: small cells and network densification, both of which are pivotal in achieving the widespread and reliable coverage required for this next-generation network. We'll pause here for now and continue in the next video. Make sure to subscribe so you don't miss the notification for part 2. Please remember to subscribe, like the video, and share it with your friends. Your support is greatly appreciated.